Hi everyone, my name is Dorra Omrani and I worked under the guidance of Kelsey DeFreites, a PhD student in bioengineering at UC Berkeley, to write a literature review on a topic that intersects space exploration and biology. So my research question is, what methods or approaches are being used to combat the adverse health effects of space radiation for space exploration missions? Now, for some background, space is full of ionizing radiation, which is high energy radiation, which has the ability to ionize atoms by removing their electrons. Now, this can be very dangerous for humans. So on Earth, we are protected by the Earth's atmosphere and magnetosphere, which only allows small quantities of radiation to pass through and reach us. However, in deep space exploration, you will venture past these protective barriers and into areas where astronauts will have minimal protection from this radiation. So, as I mentioned earlier, ionizing radiation is dangerous for humans. It can cause DNA damage both directly and indirectly, and it affects every one of our organ systems, from your nervous system to your cardiovascular system. Therefore, it's really important for us to find out ways to mitigate the amount of radiation which astronauts are exposed to. So currently, there are two main approaches taken to combat this issue. The first one is passive shielding, and this is a method where you place a material in between a radiation source and a target, and the material reduces the radiation dose, thereby reducing the dose that's absorbed by the target. The second method is a more novel method, and it's the use of biological or pharmacological counteragents. So for my methods and analysis, my paper is a literature review. So I did a lot of reading on existing literature and original research. And when doing my literature searches, I used keywords such as radio protection, radiation attenuation, radio mitigators, etc. And I used this data to compile data tables which summarize or give a holistic view of what's going on in the field. And I've put a couple of these at the bottom of the screen. So I had my passive shielding tables grouped into three types, which is traditional materials, composite materials, and biomaterials. And then my biological counteragents were classed into two types, radioprotectors and radiomitigators, based on their time of administration. So I had other criteria besides just radiation protection performance in these tables, and these are criteria that you must keep in mind before implementing these things in space. So for example, if you're looking at my materials tables, that's things like density, which is an important consideration because space exploration has upmass restrictions where you don't want your load to be too heavy because that requires more fuel and therefore more money. For my biological counteragents, this was things like drawbacks or side effects of its use. For my findings, I compared and contrasted different categories of materials and pharmacological agents, and I specifically looked at the feasibility of this application in a space environment. So again, this was looking at qualities such as density of your materials, ease of use and administration, and drawbacks. And at the end, I proposed a model which uses several lines of defense, which combines both passive shielding and pharmacological countermeasures, which has not been explored yet. So in my model, we would have traditional passive shielding materials within your spacecraft walls. So this was things like polyethylene and aluminum. And then we would use composite materials to create astronaut garments. And this would provide a second line of defense for the astronauts. And then finally, to protect against the remaining dose that is not blocked by these first two lines of defense and is absorbed by the astronaut, we would have carefully designed regimens of pharmacological agents. So that was my literature review paper, and I hope you enjoyed.